All right, now it's yeah.
Cool. Thank you. All right, so this paper is SPICEMIX. I'm going to present this paper. Yeah, so motivation, goal, method, conclusion, summary, and reference. So the motivation is really development of different computational methods can combine the spatial transcriptic data to find cell identities and spatially variable features. It still remains a challenge, and existing methods, they do not really integrate the modeling of the spatial variability of genes with their contribution to a cell identity. So, it has limitations, and, we need more robust and interpretable methods that can jointly model both spatial and cell identity factors to fully utilize, ST data, spatial transcriptic data. And
So in that paper, what is the cell identity they're referring to? Is it cell type or is like a cell location?
no,
Or
this is like spot segmentation, but this paper can apply to cell resolution if they can do it. But I mean yeah, but they do it on spot level.
do they I don't understand. Do they decompose the spot into cells, or they just annotate each spot?
They do not annotate it. They definitely they basically they do the spot segmentation. That's what they did.
Okay.
Yeah, but yeah, I'm going to talk more about it. Yeah, so the last motivation is to refine cell identities and learn spatial affinity of SPICEMIX may be useful for studying other aspects of tissue dynamics, including cell interaction.
So in their novelty, they mentioned interpretable method. Why if I recall it correctly, the method is deep learning. Why?
Well, this is not the deep learning method. So this is pretty. I mean, this is like a linear model.
Oh,
Like
so it's not okay. So it's not deep
yeah,
learning. That's what I see.
yeah.
I see.
So this is one advantage comparing to other methods that this is pretty
Okay. Yeah.
So other methods like HMF, hidden marker random field, they use HMF, before clustering. They also another method is ST-learn. They use deep learning, and base space they use Bayesian approach, and SPA-GCN they also they do identify spatial domains before doing other things, spatial location histology or other things.
Actually, multiple group members have used ST-learn before. They said like the ST-learn performance is really bad compared to others.
Yes, ST-learn it's not really good, but SPA-GCN I found it's pretty nice. It performed pretty well.
Okay.
Yeah, but I think it depends on the context, and it depends on which data set you use, and things like that.
Okay.
Yeah, okay, cool. So the goal of SPICEMIX is they try to model cellular diversity in complex tissues based on spatial transcriptic data, and they also do the latent variable modeling to find interplay of spatial and intrinsic factors of cell identity. And SPICEMIX basically improve the standard NMF, non-matrix factorization, by modeling the spatial correlation among different samples using the HMRF. By the way, I would just say HMRF because it's hidden marker random field.
Yeah.
Okay, so this is the basically the overall design for the SPICEMIX. This is basically the method based on the probabilistic latent variable modeling for joint analysis of spatial information and gene expression as well. So the first step will be the gene expression measurement, and a neighborhood graph are extracted from ST data and feed into SPICEMIX. So ST data can be from any different platforms like a Sigfish or StarMap, Vigium, or Merfish, whatever. And yeah, so SPICEMIX decompose the expression yi. Here, this is yi is the observation. This is the observed data set in cell or spot level I, and into a mixture of metagenes weighted by the hidden state xi. And this is
this model is still hidden Markov model random field. Markov random field.
Yeah, and the hidden
yeah,
this is trained. This will be trained, and yeah, they use HMRF, yeah. And yeah, basically spatial interaction between neighboring cells, neighboring spots, I and J is modeled by inner product of their hidden state weighted by sigma inverse X here, this matrix. And this matrix is basically the inferred spatial affinity between metagenes, and basically different types of correlation of latent state in nearby cells or nearby spots are captured by this matrix. Yeah, other conventional methods like HMF, they exclusively assume like a smooth spatial patterns, but this one of the advantage for SPICEMIX is it has the flexibility to represent both the smooth and sparse spatial patterns for the real tissue. And yeah, and X here, hidden state, this X matrix here, hidden mixture weight X, and the metagene spatial affinity sigma inverse X, and the K metagenes M, they are all inferred by SPICEMIX, and yeah, and they provide the unique insight into the spatially variable features, that help identity of each cell.
So the Y here is observations, right?
And yeah, then, it's the only observation data set.
Okay, so they want to factorize this into, okay, so that's why I call it now, okay. And
yeah,
right. So it's a way to okay, and then they have M is, so X here is hidden state, right?
X is the hidden state. Yeah, this is all hidden state.
And then M here, it should be hidden state to hidden state to observation. So that M here should be something emission.
Yeah, I mean they do initialize the M and X and the other parameters by using I think k-mean clustering. Yeah, I'll talk about it later. Yeah, but yeah, and then they do some kinds of training and then get the M and X. And when they do this, they use NMF and HMF. They use both of them to train the the data set.
Is X a latent representation? Like each X is a vector of a certain dimension, like 32 dimensional vector, something like that?
Yeah, so they do have like cell type composition. So it depends like how many cells you have or things like that. So I mean, so basically the dimension of Y would be number of genes by number of cells. And the dimension of M will be the number of genes by number of metagenes, and then the dimension of X will be the number of metagenes by number of cells.
Okay, thank you. So metagenes are the genes that they selected.
That part I don't really remember, but
I think it's like the X represent the hidden state, and each hidden state was represented by a list of metagenes. I think.
I mean, the X and M are all hidden states.
So actually, X is the values in X vector or gene expression of metagenes.
It's metagenes, number of metagenes by number of cells.
And what are the values? Are the values gene expression of those metagenes, or some values represent the hidden state? So is there like values in VA's Z space, or is
the X here is a cell type composition?
Okay.
It's not, yeah, I mean, it's more like a spot level segmentation. So like here you can see that because they always have, each spot has like a different, metagenes, right? So And
Yeah, can you go forward? Like, do they have like specific, more detailed equations?
okay, yeah. And anyway, I just want to also say that they do also have like a E here, the noise.
Yeah, that's arrow. Yeah, I know. Yeah.
Yeah. Okay. So this is basically the linear model. Basically, that's why I said it's interpretable. Yeah. So I'm gonna basically talk a little bit of math here. So the observations are related to the hidden variables using the potential function of is this how I mean phi is it how they say it phi, which capture the NMF formulation, and then spatial affinity between the managing proportion of neighboring cells or spots is captured by another potential function phi here. And these two different potential function phi, they together build the HMRF. And spatial potential yeah.
That's PXY, is that's the likelihood.
Yeah, this is a likelihood. And they try to maximize the likelihood.
They want to find X, so that can maximize the likelihood.
Right. They find X and they find data. Data is the parameter, by the way.
So if that's PXY, okay, that's joined Y, X hidden state in the Y. That means they have to calculate emission in the transitions.
Yeah, definitely. Yeah, they definitely do have to find the emission.
Okay, that's the emission model. Y subtract that. So that's the estimation. That's the okay. I see that. That's that. Okay, so they assume that they represent in this way. It's showing that. I see. They assume the expression is estimated by MX plus the noise. The noise is the Gaussian distributed, so that's why they can calculate this way. And then transitions.
Yeah, so basically I'm going to do the breakdown and just do it like a step by step. So spatial potential function phi here measures the inner product between the managing proportion of the neighboring spots I and J, like I and J here, weighted by the learned pairwise correlation matrix sigma inverse X, which
what is the UX and what is the
they do have like some formula, like I don't really remember what formula, but they do have some like a U formula. I thought this is like a lot of math inside of U, so I just didn't include it on my presentation. But yeah, I mean it's on the paper under the section method. Yeah, but this is a function. Okay. Yeah, I'll go on. So yeah, so this is the spatial potential function phi, a small phi here. The weighted inner product allows the affinity between two spots decomposed simply as the weighted sum of affinity between the metagens, and for the metagens to have different and learnable affinity between each other. And the cool thing for this model is that they are able to capture both positive and negative affinity between metagens. And like you guys can see that by normalizing the weight xi and xj for each spot, they can they just remove any scaling effects such as like a cell size. And yeah, so that's the cool thing. And yeah, doing this, it's easy to optimize the likelihood here in P. And observation potential function, this measures the square reconstruction error. I think this is often used in linear modeling optimization as well, so it's easy to understand. So basically, they do subtract yi with the estimated M and X. Yeah, and then sigma square in the denominator, they basically represent the noise of the NMF. And given the observed data set, they do have the model can be basically learned by maximizing the likelihood of the data. like maximizing like a function p here, and the by the way, data here in the denominator is the set of model parameters and the metagens. And so basically G data is normalizing partition function that, ensures P, function P is a proper probability distribution.
Yeah.
And
So
yeah.
this is easy to so far. Well, let me check.
Yeah, so this is not really hard to understand.
No. This part, the PXYZ, this is easy. That's just standardized graphic model, right? You have initial probability, transition probability, emission probability. But I don't understand is how the phi here, right? Why this is the transition? Why this is the emission? I can understand the emission part. I can understand the phi, but I cannot understand the phi. Then what is that? What is like the false equation?
Oh, you're talking about the function U here?
No, I just I don't understand this part. What is this? I know this is normalized, but what is this?
This is a spatial affinity matrix. So
this is the matrix.
Yeah, this is the metagen spatial affinity matrix. So comparing like the different metagens, like how close they are, how attractive they are. Yeah.
So they go back. So if that's a matrix, what is the dimension of this?
So this hold
is
on.
What is cell type by what?
Hold on. So you're talking about M, right? M.
No, this one. What this matrix, right? You have this this two. So is this M by M? Row column.
I think
it's always symmetric.
Yeah, I mean, yeah, this is symmetric number of metagens by number of metagens.
And then okay, that means okay, and then okay, and X here is okay, is a vector represents hidden state. I would say each element might be number. Suppose this one you have M.
Yeah, 1 by M, and this is M by 1.
Yeah, M by
and
1. Yeah.
You get the scaling factor at the end, right? 1 by M, M by M, M by 1. If you multiply all of them, it will be 1 by 1 at the end. And that will be just
so in other words, this is a vector, this is a vector, and then in the middle is Y, and then why not just directly do a dot product of these two vectors? Why you need this one in the middle?
Because they do have to know the correlation for each metagen, right?
Correlation.
Is it like using meta G to quantify how close or how closely these two cells are correlated?
Yeah, right. So
okay, then why you need a matrix here?
Because you have to know the correlation between each metagens, right?
Correlation between,
yeah, because you want to know how closely they are related, in the hidden stage, right? Hidden, like each spot or each cell, you want to know it, right?
Because IJ here represents two nodes, right? So in other words, if I have two nodes, I want to know how these two nodes are closely relevant to each other.
Yeah.
So so you get two vectors, each vector represents each node. Understand that part, right? Why not just directly calculate a correlation between that two vectors, or Cox cosine similarity or something? Why you need a matrix in the middle?
Yeah, I mean, if you think about it, like for example, here's spot I. This is just like a spatial transcript ST data set, right? So the vector has this ST information, like, and J also has another like a spatial information, and they, to get the correlation, how closely they are related, you have to get the matrix between each other.
Okay, and then can you go back? So how they then in that case how they learn this matrix sigma?
This hold on. This is basically trained with the metagen M here. Yeah, so X and sigma inverse X, all these three are basically learnable during the training, during the SPICEMIX training.
So If that's directly calculated, since you have the matter.
Yeah, I mean, yeah, all these three are.
Did they mention how they calculate? I don't understand this part actually.
Wait,
Everything else is pretty clear, but why I just don't get what kind of information was included here. This
Because-
actually represents the correlation between meta genes. Maybe some meta genes are more correlated. That in that case, that a certain column or certain elements in that matrix is higher, and some are lower. It's like weighted, right? It's like weight some more, some genes more, and then how do you learn that weight? I don't understand.
Okay, so maybe I mean, let's say like this. So this model basically produced the initial estimate for the model parameters data and hidden state as well. So X and data.
But then you know what? They only maximizing. They only search for X, but they're not searching for sigma here. That means the sigma is something they calculated. It's not learning. It's not learned, right?
Wait, what do you mean by sigma? Sigma here, that's when you're saying,
The sigma, yeah.
Basically, yeah, but if you think about it, you know, we input X head and, you know, data head, which are in the initial estimate, they put it here and they do maximize it. And, you know, they you know, go to the first step, which is this one. They do the iterative step. And then they lower this part here and estimate M. And if you estimate M, you will be able to get the sigma inverse X as well.
Why?
Because you know, M is basically the meta gene, you know, this. And
so once you have M's, you said you will calculate sigma based on that?
Yeah, I mean, because this is M1, M2, M3, and this is the meta gene M1, M2, M3, and you will be able to get the correlation.
Once you have M vectors, you can just calculate.
Right. Yeah, exactly. Yeah.
I see. I get it now.
Yeah.
So that's actually that's why they weighted some. Okay, I see it. Now I see it now. And then different nodes, some genes are more important than others, so they kind of emphasize more by using that instead of direct or or product. I see. It's like weighted. So it's quite straightforward method, I'll say.
Yeah, it is. And well, yeah, I'll continue. So the potential function.
So can you understand like this?
Oh, wait, are you asking me?
I'm asking them.
Okay.
So you can understand this, right? This is very standardized very standardized hidden macro, like very standardized the probability likelihood for like graphic models. Usually you have initial probability for each initial states. Then you have transitions and emissions, right? The problem now is that is how you calculate transitions and emissions, right? Like it's basically this two equation. This equation is easy, right? Just standardized Gaussian. You can clearly see that, right? This is just the estimate of noise, and then you know it's just of course it's like not the direct probability, it's log probability. And then for the problem is this part, right? This part, you know, it could be we understand, you can clearly say is some sort of dot product of two vectors, but they have one more matrix here. This matrix is putting more efforts or more weights on certain I would say certain, they call it like a meta genes.
I feel that matrix also consider the correlation between meta genes.
Yeah,
that's the metric. It is the correlation between meta genes.
Yeah. Okay. I don't quite understand the second one. I understand first row. I'm not sure about the second one.
This
is if you remember the density function of Gaussian, it's like this. Of course you have E, but then if you lock the E disappear, right?
Okay.
Did you still remember the likelihood?
I remember that, but why can we use that to represent the so we model the emission probability using a Gaussian?
Yes, that was it. So you know the Gaussian can be writing like something like this, right?
Right.
Oh, okay, got it.
Yeah, okay. then this if you do the log, right, this part will be or just a constant, right? It can be removed because you
Oh,
maximize.
so that's just noise and normal distribution.
Yes, the noise is the Gaussian distribution. Yes.
Okay. It's IID Gaussian.
Yes. So all is not clear now. Is quite straightforward model, to be honest.
Okay. So if there is no question, I'll continue. So the potential function, pi, I just want to clarify this is to capture the exponential prior on the hidden stage x.
Yeah, that's the prior.
Mm-hmm.
Prior for each all this stage random. Just yeah. Just go ahead.
Okay, so basically, we want to know x and theta. So basically, we maximize the posterior distribution of x and theta. So that's what they did. Basically solve using iterative conditional model using some kind of software out there. Yeah, so this is basically x and y is basically independent each other. So they are able to move y in the front in the conditional. Because this is the one condition in HMF, y and x should be independent to each other, and then basically they do apply log here. It doesn't matter, right? When you do the maximizing thing, and then they basically solve this. Put this state here into here, and then they solve the maximizing thing, and basically the same thing for data as well. And like what I said, they produce the initial estimate using K-mean clustering. And just want to say that about the running time, it takes around 30 minutes to 2 hours for the typical ST data set with 2,000 genes and 1,000 cells using both GPU and CPU. I forgot the name of the model for the GPU, but you can find it on the paper. Yeah, so it's not really slow. It's pretty fast, I think. And so yeah, so this is the integrated model of SPICEMIX combine both expressive power for of NMF for modeling gene expression with the HMRF for modeling spatial relationship. And they basically use both inside spatial data set, and they also use single cell data set as well. And like what I said in the previous slide, to infer the hidden state and the model parameters of the SPICEMIX, they optimize the data likelihood by through the coordinate ascent, basically alternating between optimizing hidden state and model parameters. Yeah, so I just want to quickly go over the matrix factorization. Yeah, I think many companies nowadays they use this. Netflix, Amazon, they all use this. They want to predict the how many users. I mean, which users use which items. Basically, they input the number of users, number of items together, and they basically predict the this one. Yeah, and NMF is basically non-negative, constraint for the matrix factorization. And hidden Markov.
It's just that you have a big giant matrix. You want to factorize that into multiple smaller metrics.
Yeah, right. And hidden Markov random field, I found a good definition from Wikipedia. Like what I said, yi is a random variable, and this is the probabilistic nature of yi is determined by the unobservable Markov random field xi. So xi in our data set, I said this is not observable. I mean, yeah, we don't have a data set, and xi and all other xj's independent to each other based on Markov property. And the beautiful thing about the hidden Markov model is basically they are not defined in one dimension, but it's multiple dimensions. It's within the network, so they can have more than 2 neighbors. That's a beautiful thing about the hidden Markov model. And like what I said,
that's the difference between random Markov random field versus Markov model, like classical Markov model. Because classical hidden Markov model is usually for sequence data. right?
Right. Yeah.
Or like the random field is more flexible. It could be applied to graphic data.
Yeah, that's true. Like like a classic Markov is only dependent on the previous, like a previous data set, right? But this is network thing. So
In other words, like random Markov model is for one-dimensional observation. Like one, like A, B, C, D, like something like a sequence data. But Markov random field is for graphic or graph structured data. Right? Use like you have a graph. So like one node could be dependent on or could be the parent for one could be, or the pure state for one node could be multiple.
Yeah.
Mm.
Yeah. So yeah, nice thing here. X and Y are also independent. So K metagenes are essential part of the model. They calculate spatially variable genes. And to capture the continuous nature of cell stage, SPICEMIX basically extend standard HMRF by allowing other these latent stage to be continuous. And like what I said at the beginning, it's a robust linear mixing model, so this gives an intuitive interpretation compared to other deep learning or other things.
Yeah, they're very good at writing their papers because why they mention that, because in this case you can claim the method is better than deep learning methods, because deep learning method sometimes can give you very good performance, but it cannot give you any, or it has very bad interpretability. So that's why the linear model, even though performance might be slightly worse, then the better integration. But anyway.
Yeah, also deep learning can do they also most of the times they have like overfitting problems as well. But this doesn't. Yeah. Yeah, but so the
linear models are more efficient in most cases.
Yeah. So I just want to go through a few results from using SPICEMIX. This is first one is a simulated mouse cortex data set. Mouse cortex is a reason for many ST studies. So
by the way, I highly recommend you read all this paper. Like the figures in this paper are really nice making.
Yeah, this is very cute.
Yeah, very good. It's not just this one, like all the figures. It's nice. Yeah.
Anyway, excitatory neurons in the cortex, glial cells, inhibitory neurons. They are 3 different categories for this cortex data set. Also, they introduce 2 different, spatial noise leakage, which randomly swap some read of neighboring cells, and the additive noise as well that follow random, spatially smooth patterns. And they compare with other methods, NMF, HMRF, Surat, and SPAGCN. You compare with based on the ARI. So for lower noise setting, sigma y 20%, like here, ARI of SPICEMIX was 9 to 18% higher than SPAGCN and NMF. And for the
the performance, in this case, the performance is better than all, even the other deep learning based ones like SPACEGCN.
Yeah, exactly. And the beautiful thing is when you have higher noise, like 30%, it even performs way better than the 20%. I mean, not way better, but I'm just saying that it outperforms. I mean, the pattern became more prevalent,
But this is a simulated data set. What about the real data sets? Do they show anything about?
Oh, the other data set?
Yeah.
Okay, yeah.
I don't trust the simulated data set a lot.
Yeah, they also have SIGFISH plus data set as well. Around 20. Oh yeah, 2,500 genes and 500 cells. And they first UMAP cluster the cells in the latent representation of SPICEMIX using clustering here. And they were able to find the some neural subtypes, and they were able to cluster all of them, really well. And Okay, let's look at, if you look at this map here, you get this U map here. Basically, major cell type assignments were generally consistent among all other methods like NMF and clustering, all other things as well. But the better thing about SPICEMIX is SPICEMIX uncover more refined cell subtypes and states. So basically, OPC here, OPC gene. The subtype of OPC is oligo-L, oligodendrocyte L and oligodendrocyte E, based on the stage of oligodendrocyte maturation. So, and these were basically supported by CSPG4 gene, and then other genes here, TCF and other, So they were able to find these subtypes. So that's the good thing about the SPICEMIX.
Yeah, that's why I see the figures I could see here. Not just the UMAP is nice and nice looking, and also they mark all the key information that they want to emphasize. Right here, it's like they emphasize this region, they emphasize region, and also the market. They show the genes. So it's like they actually, it's not just directly show a UMAP and ask the users to find out the information. Right, that's how we're doing that. Right. So if you guys show me the UMAP, you always just show me just that, nothing else. But instead of doing that, they actually, they highlight the key informations they want to say or they want to emphasize, so that users can easily, or the readers can easily, get that information. Right. So that's actually why people, say, oh, this is a good figure, because the information is really transparent. Right.
Yeah. Right.
And also, here you can say it's like the UMAP, the heat map they're showing is not just the ordinary heat map that you guys you're really presenting to me, right? It's like also with more information, right? You can here have different colors represent different meanings, right? And also how. So those are the things I think we should, you bring in the future when you write your paper, right? You have somehow, that's definitely a lot of tricks you can borrow.
Yeah. So yeah, like what Jun said, it has like a different colors based on different genes matching with the SPICEMIX clusters, and they do have like a number of cells for each gene for from the SPICEMIX cluster. So I think it's pretty cool. Yeah, so also from StarMap, basically the same information.
Yeah, you can see they always doing that. They always do the emphasize. So basically they want to present the information very easy to get type of mode. Like, yeah, that's, we made a lot of UMAP in the past, but we never, never emphasized it in this way.
Yeah.
Anyway.
Yeah, last but not least, it's also so I was showing a simulated SIGFISH, StarMap, Vigium. They all perform better.
Here you see that they made a lot of lines right here. You clearly see that they make all the started lines to show different regions, and how the clustering is good, right? If they don't make these lines, you may not see that clearly, right? And also they emphasize the difference of the meta genes, or they want to highlight some difference. They're using that the red regions here, right? Here, right? So that's just a kind of view aid to help the readers better understand the figure and their conclusion. If you don't do that, right, and the reviewer may not be able to get that, or then they don't trust your argument, right? You claim this advantage, but you don't highlight that. They don't get it from the figure, and then they just say, "Oh, you just randomly claim something that you don't have." Right, but instead, if you're doing those things, then the readers maybe a lot easier to get what you meant, right, and in the figure, and then they will more appreciate your conclusion.
Yeah, exactly.
Okay, yeah, that's definitely something you guys all need to remember and to practice in the future.
Yeah. Anyway, yeah, cool feature, nice paper. Yeah, so the conclusion, it's the integration of matrix factorization and spatial modeling in SPICEMIX yield better and robust inference of spatially variable features, both sparse and layer specific, that underlie cell identities as compared to existing methods in many different data platforms. So they can apply to any different platforms. That's another good thing. They improve, sparsity constraint on NMF, on standard NMF, and then they also improve HMF. HMF used to have the weakness of missing sparse cell types and smooth across layers, missing even the layer-wise structure of excited neurons, but they fixed that. Yeah, so like what I said, conventional HMF have the cell types or spatial domains discrete. That's the problem. Another problem is it exhibits smooth spatial patterns, which is not true of many cell types, and they fixed that in the SPICEMIX. And SPA-GCN, they improve graph convolution neural network SPA-GCN. Like what I said, SPA-GCN is susceptible to overfitting, and it's hard to interpret compared to SPICEMIX linear model. So yeah.
And we also our group also has a model from here, and we build actually SPACE-GCN.
Okay.
A lot, yeah. So performance our method is better actually. So yeah. Anyway, so we should present her work later on. You probably can see that.
Yeah. So I just want to basically I just made some comments. This is basically repeating the same thing.
Your strengths, right? But then I'm more interested about your thinkings about how we can make it better.
Yeah, so this is some of my thoughts from the paper. ARI average of 575, 57.5%, in the real 10x, data set. So it can definitely need improvement for sure. And then, add spatial patterns of individual gene might help. They do have spatially variable metagene formulation, but they do not have the individual gene in the spatial patterns. So, adding those kind of information might help.
Is this your thinking, or their comments in the conclusion part?
This is their comment here, this part here, in the parentheses. And I found this thing. They didn't really say that they were going to add it, but, I thought that adding spatial patterns to individual gene might help.
Okay.
All right. And, supervised method can be utilized together because this is unsupervised. If you have the, data sets with targeted panels, by a prior knowledge, using, 10 gram or whatever to align, a spatial and the, single cell RNA-seq together, they will be able to increase the power, right? And it's also great interest to model the dynamics of spatial pattern across,
yeah.
So
the last point you mentioned here, like cell interaction and that, and clustering, and that is exactly what Zhou is doing. We don't think it's a good idea to segregate the cell interaction inference and also the spatial clustering inference. So instead of doing them separately, we put them together in one model.
Yeah, right. And we don't have time so much, so I'm going really fast about my project. So basically, I'm doing the cell type decomposition. SPICEMIX is the spot segmentation, and what I'm doing is cell type decomposition. So it's a little bit different, and so this is where SPICEMIX belongs to, region segmentation, ST-learn-Seurat and SPA-GCN, SPICEMIX, all other things here. And what I'm trying to do is cell type deconvolution, and there are many people also working on this cell type deconvolution nowadays.
And they're all very good papers. That's the one.
They are all from Nature's or things like that. So get the single cell, get the ST data set, combine them together, get the cell type deconvolution for each spot. That's what I am trying to do. So get the basically typical, variation of VAE or AE, decode it, and then combine all cell type latent layers together here, and then apply the same thing here and get the hidden layer here as well, and try to minimize the loss between these two. And many data sets. I'm currently working on the lymph node Visium data set right now, but there are many other sets available. And if you guys need any data set, like a filter data set, I do have all of them ready. So you can always ask me. So. Yeah, and then this is the reference for this presentation.
Yeah, very good, very good. Any questions, comments?
Can you go back like 2 slides? I'm
Yeah.
just gonna look at that, but yeah, but everything will be good otherwise.
Yeah,
But here, one important thing is that you never know the correspondence between the cell on the left side and the cell on the right side, or spot on the right side. So how do you know find the correspondence spot for the cell, or the other way around? So the loss here is not that easy to I got your point. You're saying you want to minimize that, but then aligning them, right? Aligning the C and S might be challenging.
yeah, definitely. Yeah.
Anyway,
All right.
Doesn't this look like the Eurasia? It actually like that's like
yeah.
zone type 3 looks like the world. That's it.
Yeah, this one like U.S. continent, like North American continent.
But it just looks like upside down. Like that's Australia, that's Africa, that's Europe, and that's like Russia and Japan.
I think maybe they use it just
Yeah.
choose to reference.
Maybe.
Anyway, there might be. Who knows? Yeah, could be.
Yeah.
Anyway, any other comments? No. Okay, very good. Who is the next one?
I'll be going next, and then I'll check with you when we meet on Wednesday about the paper.
For sure, yeah. We might still have to meet on Zoom. I'm not sure where I'll be on my office, in my office on Wednesday. Yeah.
Well, let me
But
know.
we'll let you know at least by Wednesday morning. All right.
Okay.
Whether the meeting will be in person or not.
Sounds good.
Yeah. All right. See you guys.
Oh, June, do you have time like a 5 minute after this?
No. I have another meeting at 4, so we have to talk some other time.
Maybe 5 or today later? Do you
No,
have...
we have regular meetings at Tuesday, right?
I mean, tomorrow we have a meeting, but I just want to ask like a quick question, like a one question.
One quick question. You can just select me your question and I will answer when I get time. I have quite a few meetings today.
Okay, sure.
All right. See you guys. Bye.
See you.